Hi, Max. Okay, so this is the situation. So we're going to assume that we've got an air temperature of 68 degrees and that the living body's temperature is 98.6 degrees. And so how does the rate of change of something cooling occur? Well, basically, it's kind of like a little bit of an exponential situation, right? The hotter something is, the more it cools. Right? So it's kind of like you look at the kind of the difference between the thing being the hot thing and the ambient temperature, and the rate at which that goes down is proportional to the difference in the temperature. And it turns out that this thing here, this formula there, gives us what the temperature of the body will be, right? So here's 68 degrees. That's what the ambient temperature is. 30.6 degrees, right? That's the difference between the body temperature at the start and the room temperature. And then it sort of that difference decays exponentially. So that's the model that we're going to use. So one of the things that you'll learn is that because you can use a tangent line, you can come up with rough sort of rules of thumb of what quantities are, okay, by assuming some kind of linear dependence. So for example, coroners estimate that a body cools about 2 degrees during the first hour of death and about 1 degree for each additional hour. Okay, so what I want you to do is, if you go to Blackboard, you can see this file here, coroner. And that will do this, this scenario for us. So this exercise is just an exercise in using Excel in just modeling something. Okay. So, hi, all the people there. Hello. It's okay, you're here. Okay. So we're going to model the scenario here. So what I've done is I've set up an Excel file. And so what you see here is we've got a grid of points. So each row corresponds to a time since death. And you can see that the grid that I'm using is 0.1 degrees. Okay. And so here I've put in that formula, 68 plus 30.6 times exponential of minus k to the t. Why is it flat? Can anyone, looking at that, can anyone tell me why at this moment it's flat? We don't expect it to be flat. What's causing that to be flat? I put the 0 in here, yeah. If you put the 0 in here, this makes this 1, so it's just going to, so that's just going to be 98.6. So this is assuming that there's no cooling yet. Okay. So so what I want you to do, the first thing we've got to do is we've got to find a value for k. So we're going to use that rule of thumb to be able to figure it. So I want you now with a piece of paper to figure out, okay, we've got 68 plus 30.6 e to the minus kt. So what I want you to do is to solve, or when will the body be 96.6? And t is going to be 1. Okay, so this is, so we can get rid of that 1. Okay, so this is the rule of thumb. We can use that to find k, and k is the rate at which we're going to, at which the body loses temperature. So have a go at that. So this should be something that you remember from that first chapter. What's the first thing we should do? So let's do some algebra here. So what's something we can do? What's the first thing you would do? Yeah, we can subtract the 68 and we get 28.6 equals 30.6 times e to the minus k. What's the next thing we should do? Remember, we're trying to isolate the k. So what's the next thing we should do?
Divide by 30.6.
Divide by 30.6. Exactly. What's the next thing we should do? How do we get rid of the e?
Log.
Yep. We do ln. And the last thing we should do is get rid of the minus. And minus log, well, that's just the same as inverting. And that gives us an expression for k. So we'll now go to the Excel file, and now we know what to put in for k. So hopefully you've all gotten the Excel file. Okay, so now we're going to put the first thing in. We're going to replace 0 by equals, oops, sorry. What have I done? Okay, replace the zeros by equals ln, and then in brackets 30.6 divide by 28.6, close brackets. And there we go. And now we see what we expect to see, right? We expect to see exponential decay. We expect to see exponential decay down to 68 degrees. Okay, and if we look at the column, what do we see after 1 hour? What is the temperature? 96.6. It's gone down 2 degrees as promised, so everything is good. Okay. So now we've got a working file that we can use to answer questions about the situation. Let's go back to our sheet. Okay, so we did algebra. We did number 1. We found the value of k, and we put the k in there. Notice what I did. I didn't use a calculator to figure this out and then put that in. I actually did the actual calculation in Excel, right? And that way I got an accurate answer. So I stopped any kind of rounding error by doing that. Okay. Okay. Next, we want to put in the rule of thumb. Okay. So we want to do it for -2 degrees per hour for the first hour and -1 degree per hour for the subsequent hours. So how do we go about doing that? Okay, so let's go to the Excel file again. Okay, so we want to put in a new variable. So what we should do is if we click on the third variable and we put in insert, it will create a new blank column for us. And I'll call that column C. That stands for coroner's rule of thumb. So in here I want to put in our linear approximation. Okay, so I want to go from 98.6 to 96.6 in the first hour. And I want to do that linearly. Okay, so how do I put something linear into Excel? Well, how do we do things linearly? So what's the thing that determines that you've got a linear function? What happens at each step? Linear functions have constant what? Rate of change, which is the slope, right? So it goes 98.6 to 96.6. So if it's a linear fraction, it's going to go down by the same amount each time. So we want it to go -2 in 1 hour. Okay, so we want it to be -2 degrees per hour. Okay, so if it's doing -2 degrees per hour, how much does it go down by every 1/10 of an hour? -2 degrees in 1 hour means what minus what in 0.1 hour?
0.2.
0.2. Okay, so that's how we can do it. So we can just go here, and in cell C3, we just put equals C2, because that's what the previous thing was, and we just do minus 0.2. And then we just copy and paste, and it does it for us. Okay. Now we want to change it going from minus 2 degrees per hour to minus 1 degree per hour. So if it's minus 1 degree per hour, what is it per tenth of an hour? Elijah? If we're losing 1 degree in an hour, how much do we lose in a tenth of an hour? 0.1, yep. And so we just do the same thing. So we go to cell C13, which corresponds to 1.1, and we write equals C12, because that's the previous hour, and now we're just going to subtract 0.1. And then we copy and paste all the way down to the bottom. And then we can double check to see that things are working good. Right, after 2 hours, it's at 95.6. At 3 hours, it's 94.6, etc. So we've done it. We've come up, we've put in the rule of thumb. Okay. So let's graph those. So I'm going to highlight both columns, and then I'm going to go to Insert, and over here, so you see this thing over here? That's where the line is. So we just put that, click that, and we're just going to do this. Okay. And so there we go. That's graphed both of them. You have to play around with it a little bit to get it more properly, but we see that we've gotten that at the beginning it gives us very good answers, and then in the middle not so good, and then at the end we can compare our rule of thumb. So remember, the rule of thumb is just something you can do in your head, whereas the formula, you'll need a calculator or something to do. So everyone try that. So try that with your Excel files. Let's see if we can get that to work. I don't know how to do that. So are you able to get it to look like that? Oh, great. Yep. Elijah? Yeah, so okay, so go back to it. Is it subtracting by 1? Oh, so go back to the 2, to the 1. Okay, so do subtract minus 1. So you can say equal C12 minus 0.1. Okay, now, and then copy and paste that. How are you going? Yep, okay, you're doing good. Okay. Let's see what else we got. Okay, so we did number 4, but we didn't do number 3. So let's take the derivative of t and find out when is it actually moving at minus 1 degree per hour. So if our t equals, what is it, 68 plus 30.6 e to the minus kt, what is the derivative of t equal to? Okay, so what happens when we take the derivative of the 68? It's 0, right? Then we got the derivative of this. So the 30.6 stays because that's a constant multiple. That stays because it's a constant multiple. This goes away because it's a constant addition. What's the derivative of an exponential? You'll need this for the test tomorrow. The derivative of an exponential is the exponential itself, right? So first thing we write down is e to the minus kt. And what do we put here? Negative k. Exactly right. Okay, and so we want to solve when minus 1 equals 30.6 times minus k times e to the minus kt. So we want to find out, we want to solve for t. Okay, so we can get rid of the minus signs. And so we get 1 divided by 30.6k equals e to the minus kt. We can get rid of the minus by reciprocating, so 30.6. Remember, k was ln of 30.6 divided by 28.6 equals e to the kt. Get rid of the e by doing the ln again, so we get ln of 30.6 times ln of 30.6 divided by 28.6 equals kt. And then finally we can divide by k, which is ln of 30.6 divided by 28.6. So it's a whole mess, right? But we can all just do it in Excel and to find out when that is. Does everyone follow what I just did that? I just did a whole bunch. So the whole point of when you do solving algebra is you just undo everything. Here it's multiplying, so I divide. Here I've got a minus, so I reciprocate to get rid of it. Here I've got an exponential, so I take a log to get rid of it. Here I'm multiplying by k, so here I divide by k. So I'm just undoing everything. So let's solve that. So let's just solve it here. So equals ln of 30.6 times k, but I know what k is actually because that's in D2, times D2 divided by D2. So that's easy. And I get 10.75. So that means at around 10 hours, 10.7 hours, it's losing 1 degree per hour. So if we go to 10.7, right, and we see that's actually true, right? Because at around 10.7, we see that here it lost around 0.1 degree when going backwards, and like we go from 82.94 to 82.84 to 82.74. We see that it's losing 0.1 degree per 0.1 hour, just like we expect. So at around 10 3/4 hour, the graph of our function we go back here, at around here, the slope here, I'll get my pen. The tangent line here is losing around 1 degree per hour. And over here, this line here is parallel to there at around 10 3/4 hours. Right, so that does that first thing. So we can now go back to what we did. And so all we've done is just model the situation. Okay, so we've seen, so we've put in the actual case, and here is in red that rule of thumb, and so we can see that around here and around here, it gives us a good estimate. And then in between here, it gives us a slight overestimate for what the temperature should be. But it's, at most, it's just off by maybe a degree. So we can figure out when it gives a good estimate and when it gives a bad estimate. So that's the kind of thing you can do with these linear approximations. So here's another situation where things decay exponentially. And that's with air pressure. So that's why when explorers go exploring off in the mountains, they take barometers with them. So the idea is that by comparing air pressure at the bottom of the mountain to the top of the mountain, that can give them an idea of how tall the mountain is. Of course, the barometer, it also depends upon the weather, so you've got to take that into account. Okay. But again, air pressure is something which sort of decays exponentially. So at sea level, the air pressure is something like 30 inches of mercury, and as we go up, it decays kind of exponentially as we go up. Okay, and so in question 2, in the second one, it's just basically doing the same thing that we did with coroner, except doing it with altitude. So let's take our Excel file and change it to this problem. So we want to change it to pressure equals 30 times e to the minus 3.23 times 10 to the minus 5 h, and we want to use a delta H of 10. Okay. So let's go here. So let's change this to our situation here. So let's change this to P. And this to H. This to delta H. And then we're going to change this to 10. And to K, we're going to change to 3 point. Now, if it's 10 to the minus 5, that means we've got to do 1, 2, 3, 4, 5. 3, 2, 3. Is that right? 1, 2, 3, 4. Oh, no, sorry. It's 4 zeros, right? We're taking the 3.23, we're moving it back 5 places. So that means we enter in 0.000323. Okay. And then let's put in our pressure function. So we should get rid of this. Change that to a 30. And then copy and paste. Well, let's get rid of this thing here because we don't need it anymore. Let's cut that as well. Right, so in this one here, the rule of thumb is that the pressure drops 1 inch for every 1,000-foot increase in height. So if it drops 1 inch for every 1,000 feet, how does it drop every 10 feet? Anyone? It drops 1 inch in 1,000 feet. How much does it drop in 10 feet? Minus 0.1. Well, that's a tenth, right? What's the relationship between 10 and 1,000? 10 is not 1/10 of 1,000. 10 is what proportion of 1,000? 100, yes. So it drops 100th of a feet. So if we go back here to our thing, we're going to start off at 30. And now we're going to drop 0.01. And now we copy and paste that. And so now we've done the same thing as before. We've got an exact model here. And we've got a rule of thumb right there. Okay. And I think the rest of it I'll leave just as a homework to do. Any questions about any of this? Any questions about the test tomorrow? So hopefully you've all been practicing your differentiation. So, I mean, what's going to be on the test? I'm going to test those rules. That's what we did in chapter 3. What did we do in chapter 2? We figured out there was some economic stuff. What was 2.4, section 2.4? Oh, section 2.4, oh, second derivatives, that's right. Okay. So stuff about second derivatives, stuff about economics, and then stuff about using the formulas. So that's what's going to be on the quiz tomorrow. Okay, everyone? I have a thumbs up. Excellent.